let's see. Last time we started talking about sets, and then we defined some notions. In particular, we defined the notion of equality, and then we defined the notion of subset, okay, and proper subset, and related terminology with that idea. Let's just continue with this. But to continue, let's actually pause and prove a little theorem, and we kind of hinted at that last time, but let's do it now. So theorem. So for any set, so let A be a set. This can be whatever set you want. Then there are two things that we can always say for sure. Number one, the empty set. Remember, this is a special set. This is a set that has no elements. It's going to be always a subset of any other set. So no matter what A is, the empty set is always a subset. In fact, okay, it's always a subset. And then number two, the set itself is always a subset of itself, of course. I mean, these are very trivial statements, okay? But the point is that any set always have two subsets. I should say at least one, because if A happens to be the empty set, there's only one subset itself, and then that's it, okay? But any non-empty set, it always have at least two subsets. The empty set is always in there, and the set itself, okay? Now it could have more, depending on what the set has, okay? So keep that in mind. Let's prove this. So proof. So let's prove number one. So we kind of discussed this last time. This one actually is like a vacuous proof, okay? So I'm gonna give you two ways of doing this. Let's first do the element-wise approach, okay? So actually not the element-wise, but by contradiction. Usually, whenever you have a statement that deals with the empty set, you try to do it by contradiction. Okay? In other words, what does it mean to prove this by contradiction? And we assume the opposite. Okay? So assume that the empty set is actually not a subset of A. Okay? We want to show that this guy is a subset of A. Let's assume the opposite. Let's assume that it's not a subset of A. And now let's work with our definition. So let's see, who can remind me what does subset means? What's the definition of subset? When you say that A is a subset of B, what does it mean?
Everything in A must be in B.
Exactly. So if A is a subset of B, what's the definition? If X is an element of A, then X will be an element in B, right? Every element in A is an element in B. Okay. Therefore, if we are saying that the empty set is not a subset, what does that mean? So what follows from here? What can we conclude? What can we say for sure?
There is an element in the empty set that is not in A.
Exactly. So what's the negation of being a subset? So how do you negate this? It means that there is an element in A that is not an element in B. Right? That's what it means to not be a subset. And this guy has something that this one doesn't. Okay? So if the empty set is not a subset of A, then that means that there is an X is the empty set, and this X is not in A. Do you understand this? Okay? But as you know, because this is a statement, in particular, this means that there is an X in the empty set. So then there exists an X such that X is in the empty set. But what can we say about this? This is false. So this is clearly a contradiction, right? I mean, this makes no sense. There's no element in the empty set. This right here is false. So this is a contradiction. So if we arrive to a contradiction, that means that our original assumption must have been wrong. So our original assumption was that the empty set is not a subset of A. So then what can we deduce? It has to be, right? So therefore, the empty set is a subset of A. So basically, the idea here is you cannot prove that it is not a subset, because if you tell me it's not a subset, that immediately tells you that there is an element here in the empty set that's not in A, but that's a problem. If you cannot find such an element, then it has to be a subset. Okay, that's vacuously true. An alternative here is just to go with the definition. So alternative is just to say, okay, look, empty set subset of A. What does this mean? Let's just write the formal definition. This means that for all X, if X is in the empty set, then X is in A. So this is equivalent, saying this is equivalent to saying this, to saying that this is true. So if we manage to show that this statement here is true, then that means that the empty set is a subset of A, because it's a definition. Okay? Now, right here, you can immediately see that indeed this is true. What can we say about this part here? As false. So no matter what X is, that's always false. So what can we say about this whole implication? It is automatically true. So for every X in whatever domain you have, okay, whatever universe you have, then this implication will always be true. Therefore, this is a true statement. Okay? So this is what we call a vacuous proof, because there is nothing, it just vacuously happened because there is no element for you to disprove this that you can use to disprove this. Okay? So, moral of the story, the empty set is a subset of every other set, including itself. Okay? So it's important. If A is not the empty set, then we could also say that the empty set, so I guess let me say here, if A is not the empty set, then we can improve this a little bit more and say that the empty set is a proper subset of A. Because if A is not empty, it means it has something inside. So it's not just a subset, but we can say also it's a proper subset, right? Because A has something that the empty set has. I didn't write it originally because this could be the empty set, because A is any set, and then, the empty set is not a proper subset of itself, because proper avoids equality. Okay, any questions about number one? All right, so let's take a look at number two. So how do you prove number two? So we want to prove that A is a subset of A. So how would you formally prove this? This is just a line, just one line. In other words, when you want to prove that a set is a subset of another set, what do you think you need to do? What's the formal way of doing it?
Element X. If there's an element in A, then there's an element in B.
So exactly. So this means this, right? Means that this implication is true. So that means that if you want to prove that A is a subset of B, you need to argue that this implication is a true statement. So now focus on that. You already know proof techniques. How do you prove that an implication is true? What do you do? This is your P and this is your Q. How do you prove a statement of the form P plus Q? You assume P, you prove Q. So you need to assume. What do you assume? Assume P, which in this case is assume that X is in A, and then you do some work, and then eventually you want to prove Q. In other words, you want to show somehow that this same X that you started in A now is in B. You understand this? It's always the same thing. When you want to show that something is a subset of something else, start by assuming that there is an element here, and then show that that element somehow is also on the other side. Okay? So if I want to prove this, all I have to say is, well, let X be an element in A. I don't care what's not in A. I'm only focusing on what's in A. Okay? Now, what do I need to choose? What do I need to prove? Well, I need to prove that this element is over here. But what is this? A. So of course it's there, right? Like I said, just a one-line, stupid little thing, but it's just for you to get a feeling of the formula. Okay? So let X be in A, then, well, X is in A. Nobody can argue this. Okay? So A is subset of A. Do you understand what this is saying? Again, it's not because this itself is important. I mean, this is obviously true, but this actually tells you how you prove that one thing is a subset of another. Okay? Start with an element on the left side, and then do some work and show that that same element belongs to the right side. That's called an element-wise argument. Okay? In this case, there was no work to be done, but usually there is some things that you need to do. You okay with this? All right. So moral of the story: the empty set is a subset of any other set, and every set is a subset of itself. Okay? So remember that. Here is another theorem. It's a characterization of equality. So who can tell me what equality between two sets is? If they have the same elements, right? Two sets are equal if they have the same elements. Now, if you're working with abstract sets, what operation do you think you need to test to verify this? In other words, let A and B be two sets. Then A is equal to B if and only if what? What do you think is an equivalent condition for two sets to be equal? They have to have the same elements. In particular, what does that mean? Every element in A has to be an element on B, and every element in B must be an element in A. Yes? In other words, how do you write that now with operations that we know?
A is a subset of B and B is a subset of A.
If and only if A is a subset of B and B is a subset of A. You understand this? So from now on, and this is what we do in mathematics, if you want to argue that two sets are equal, this is what you do. You show that the left is a subset of the right, and you also show that the right is a subset of the left. And then you're good to go. Is that okay? Now, to prove this, it's very straightforward. So proof, we're just going to use definitions and some logic. So let's start with the left. A equals B is equivalent to say, so this happens if and only if is definition. What does it mean? It means that for all x, x is in A, if and only if x is in B. That's the definition of equality. That's how we define equality of two sets. That's what it means that they have the same element. But now, let's use logic. What do we know about biconditionals? What do we know about biconditionals? This is the same thing as saying that x is in A. So, P implies Q, and Q implies B. Remember that the biconditional breaks as two conditions, right? So P implies Q, so the conditional and is converse. That's what it means. That's why we use two arrows, because it goes both ways. Okay? So now, if you remember, when you have a universal quantifier, for all distributes over n. So this is the same thing as saying this is logically equivalent, or I'm just writing the equivalent symbol. If and only if for all x, x is in A implies x is in B, and for all x, x is in B implies x is in A. So at this point here, I would just say this is logic. This one right here is a step from logic. We're using the fact that for all distributes over n. But now, what is this right here? What is line? That's the definition of what? We have right here. That's the definition of subset. That means that A is a subset of B, and what is this line over here? That's the definition that B is a subset of A. So this is the proof that this is the same thing as this. Okay? So from now on, if you want to show that two sets are equal, this is one approach, and this is typically the one that we take. If you want to do it element-wise, what you do is show that A is a subset of B and that B is a subset of A. Okay? This is when you work with it abstractly. I mean, if you are given the sets, A is 1 to 3 and B is, whatever, just look at it and you can see if they have the same elements or not. But in an abstract sense, this is what you need to argue. All right, questions? All right, so we're gonna come back and we're gonna do more examples in proving equality and so on pretty soon. All right, so now that we know this, we know subsets, we know equality, let's keep on talking about more ideas about sets. There is a notion of cardinality, okay? And the cardinality gives you a sense of the size of a set, okay? Now, cardinality is a little bit complicated, not a little bit, it's very complicated for any set, because the point is that sets, they have elements, and when we say cardinality, it's supposed to talk about how many elements does it have, okay? Now, when the set is finite, it's easy, just count, and then the cardinality is how many elements it has, the number of elements. But when the set is infinite, it's no longer how many elements it has. We talk about the size of the set. For infinite sets, size is not the same thing as amount of elements. For example, we're going to see later on that the natural numbers, which are 0, 1, 2, 3, etc., and the integers, just 0, 1, 2, 3, etc., together with the negative guys, right? Let's see, which one has more elements? Which one has more elements? This one has more elements, right? Because, it has all of these guys plus the negative pressure. Nobody can say that this one has more elements. However, they actually have the same cardinality. They have the same size. So when we're talking about infinity, you have to be more careful. The naive notion of size is not the same. Now, for finite sets, when you say size, it's the same thing as what comes to your mind. Just count the elements, how many elements it has. If it has more elements, this one is big. It has a larger size. But for infinite sets, it's not the case. We have a section that we're going to talk about infinite sets, okay? We're not going to go too deep because there's a whole discipline on its own. But we're going to, get some idea of what are the questions that we're interested in here. Anyways, we're going to get there, but for now, let's just take it slow. So let me say cardinality of a set. And right here, right now, I'm just going to talk about finite sets. Infinite sets, we're going to worry about those later. So definition, if a set A, if a set A has exactly n elements, so n distinct elements, they have to be distinct. Okay? Then we say that A is finite. Then we say that A is finite. Here, n, of course, is a natural number. Then we say that A is finite, and n, this is cardinality. In other words, in the case of finite sets, cardinality is exactly the number of distinct elements. So we write, and let me say, so if A is not finite, we say it is infinite. I'm going to leave it at that. Later on, we're going to come back to this notion, what to say about the cardinality when in the infinite case. But right now, let's just talk about the finite case. Okay, so notation. So we're going to use the absolute value symbol for cardinality. This is the one that's typically used. In some places, you will also see this. Okay, but the most common notion is this one. Like this one just to indicate number of elements or something like that. That's why we put the n. But this is the most common notation with the absolute value, and that's the one that I will be using. Okay, and that's the cardinality for cardinality of A. So if A has n elements, and when I say n elements, I mean distinct elements. Okay, I don't want to write the word distinct again. If A has n elements, then the cardinality of A is n. Okay, I guess let me give you an example. For example, if A is a set 1, 2, 3, what's the cardinality of A? It's 3. Okay, so all right, so cardinality of A is 3. Any questions? Okay, good. Actually, let's see another example. What's the cardinality of the empty set? 0. So the empty set is the only set that has cardinality 0. Any other set has cardinality a positive number because it means that it has something inside. You understand this? All right. All right, let's see. What's the cardinality of the set containing the empty set and the set containing the empty set? What's the cardinality of this? This is 2. There are 2 elements here. What are the elements here? This is one element, the empty set, and this is the other element, the set containing the empty set. Do you understand? I mean, it's simple, but it could be tricky, so you have to be very careful. Yes? Okay. All right. So that's 2. By the way, this is actually one way that people used to then when we started to formalize number system. This is one way that actually we used to build the natural numbers. Like for example, using the axis of set theory, because we can say by looking at the cardinality, the number 0 is the cardinality of the empty set. Then to make the number 1, what we do is we look at the set containing the empty set, and we look at the cardinality of this. What is this? 1. Then to make the number 2, we look at the set that contains the empty set, the set that contains the previous sets that we have written down. Okay, because we have an empty set, then I can make this set. Since I have these two sets, now I can make this set. What's the cardinality of this? 2. And if you want to build the number 3, because we know that these 3 sets exist, because we started with the action that the empty set exists, therefore this one exists. But then if these 2 exist, you can build this one. Now you can build the next one. What will be the next one?
Empty set, set of empty set.
The empty set,
Set of empty set.
the set of the empty set, and then the set that contains the empty set and the set of the empty set. What's the cardinality of this? 3. They have 3 elements. 1, 2, 3. Yes? And so on. Then you can build 4, 5, 6, and so on and so forth. Okay? This is how you formally can build the natural numbers once you introduce formally what sets are. Okay? Because one of the axioms is, because who tells you that these things are real? I mean, I know this sounds a little bit weird what I'm telling you, but do you know this? Who was it says this? Descartes, right? You know this famous expression, I think, therefore I am. Where did that come from? Because there was this theory that why there is an evil demon somewhere and that everything is an illusion. How do you know that I'm real? How do you know that I'm real? Could be in the matrix. I mean, how do you know that all of these things is real?
Let's try it out.
But then what he said was, well, I don't know if you are real or if you guys are real, but I know I'm real because I can think. Okay, I'm thinking, so I can make decisions for myself. I think, therefore I am.
Are you sure about it?
So, in the case of numbers, how do you know that sets exist? How do you know that a bag of milk and a bag with milk, cookies, and whatever stuff like that exists? Collection of elements. How do you know that numbers exist? Yeah, but you can think about many things. It doesn't mean that they exist, right? Those things that you think about. But then that's why we need the action. There is at least one set that we call it the empty set. The set that has nothing in it. I'm not relying on the fact of all the stuff to exist to make my set. Because if you say the set containing 1, 2, 3, then you need to say, yeah, but what are 1, 2, and 3? I don't know. I mean, I'm getting to philosophy now. This is a philosophical issue what I'm talking about here. How do you know that the number 1 exists? The number 2, the number 3? But what we say is, okay, there is a set that has nothing inside. If you tell me that nothing exists, then there is a set that has nothing inside. Okay? But once you establish the existence of this set, that you assume this as an axiom, now you can make sets with stuff inside, and these ones. Now I can make a set with this stuff that we said that exists. Then I can make another set with these 2 things. And inductively I keep on doing this. And this way, then we define, okay, 0 is the cardinality of this first set. 1 is the cardinality of this other set. And so on. So now we have established that the numbers 0, 1, 2, 3, etc., they make sense, they exist. No matter where you are, no matter what planet, what universe, what alien race you are, you can prove to them that there is a notion of 0, 1, 2, 3, 4, etc. I know I'm going beyond to what you may be used to in a math class, but this is what it is. Math, philosophy, logic, all of the things, they go together. Okay? At some point, they start branching out and so on, but their roots, they're all the same. That's why at the beginning, the Greeks, they were everything. They knew about math, they were philosophers, they were physicists, they were chemists, because everything started together. Then, as civilization started to grow, then things started to take their own separate ways. Okay, and so on and so forth. So here's one way that we can make sense of the number 0, 1, of the natural numbers. Okay, so that's cardinality. And I guess I would say, as an example of an infinite set, so the natural numbers, which is the set 0, 1. Now that we have established the existence of this, we have the right to say this. Okay, now we know how to make sense of these numbers. This is infinite. Okay, we will return and say something about the cardinality of this guy later on. For now, it's not finite, so it's infinite. We okay with this? All right, so let me introduce another notion. Given a set, there is another set that we can make out of it. which is what we call the power subset, the power set. The power set is a collection of all possible subsets of the set. Okay? So, for example, the power set of this guy will be all possible subsets of this. What would it be? It would be the empty set, okay? And then itself, the set containing the empty set, okay? The power set of this one is a little bit more complicated. It has 8 elements, okay? We're gonna discuss that right now. So let me talk about that. So power set. So definition. Let A be any set. Then its power set. And its power set, I'm defining this, is the following. So the notation that we use is like it's not a capital P, but it's like a script P or something like that. Okay. So the power set of A, by definition, this is the following set. It's a set, the collection of all B's such that B is a subset of A. In other words, it's a set whose elements are all subsets of A. So in words, is the set of all subsets of A. Okay? So for example, let me give you some examples right now. Let's say that the example with A equals the empty set. Let's compute its power set. Then let's compute the power set of the set 1, 2, 3. And then let's compute the power set of the set 1, 2, 3, 4. And then hopefully you will see something interesting happening here. All right, let's see. For them, and by the way, okay, so the empty set. What's the power set of the empty set?
The empty set.
What's the power set of the empty set? So power set of A here is the power set of the empty set. What is this?
The empty set.
Why? Are you saying the empty set has no subset?
That's all one.
So it's not an empty set. It has an element. It's the set containing the empty set. Remember, it's just all possible subsets of this guy. Now, what are the subsets of the empty set? Just the empty set. Remember, we just proved the empty set is a subset of everybody, right? So in other words, power set is never empty. Doesn't make sense to say that the power set of something is empty. The empty set is always an element in there, because the empty set shows up as a subset everywhere. Do you understand this? We proved it. Okay. For number 2. So in particular, notice that this is not empty. Okay? I want you to notice that it's not the empty set. Okay, so number 2, what would be the power set of A? We have to make all possible subsets. If you want, let me do here, I guess, 1B. Let's do it with one element. So what would be the power set of the set containing the element 1? What is this? You have to list all subsets. What are all subsets?
The empty set and 1.
The empty set and the set containing 1. You have to be careful. The elements inside the power set are sets, not just elements. Okay, so you have to put the little curly braces. Do you understand this? Okay, good. So in general, in fact, the power set of A always contains the following elements. So a subset of the power set is this set. In other words, what I'm saying here is that every element here is an element in this set. So every time that you write the power set of something, you will always have at least 2 guys, the empty set and the whole set itself. Now, there could be more stuff, okay? Keep in mind that when A is the empty set, it's not 2, it's just 1, because the A is empty, these 2 things, this is just the same as this. Remember, repetition is not important, okay? So when you're listing the power set of a set, always understand that you need to have the empty set, the whole thing, but then there could be other stuff, okay? So let's practice how to find that other stuff. Like in this case, it was the empty set and the whole thing, because there's nothing more to do. But let's take a look at this one. So I know for sure that my empty set, the empty set has to be in the list, and the whole thing has to be in the list. Yes, because they are all subsets of A. Now you have to find all other subsets. So what are all other subsets that we can write? Set containing 1. Okay, the set containing 1 and 2.
Two and three.
Okay, let's try to give it algorithmically or systematically. Why? Because now I give you a set with 10 elements, you're gonna go crazy trying to see. In fact, you're gonna have 1,024 elements inside that set. So if you don't have a plan on how to write them down systematically, like our truth tables, we had a systematic way of writing our combinations of true and false, so we know that we're not missing anything. Okay? So let's try to establish a systematic way. And for example, in the one that I'm gonna explain you, this one will come in last. So I'm gonna erase it. So here is what you can do. We start with the empty set because that's there regardless of what's happening. Now here's what we're gonna do. We're gonna go by length, by amount of elements. Okay? Yes, by amount. Should I go by amount of elements? Or the first guy and then
The first, second, third.
Yeah, I'm going to go by length. So elements of length 1, what are they?
1, 2.
Would be 1, would be 2, and would be 3. I wonder if I wanna tell you this. Yeah, okay, by length. So 1, 2, 3. Now that's all possibilities for length 1, right? Now let's exhaust all possibilities of length 2. And to find them, here's what you do. We're gonna start with the first element, and we're going to combine this guy with everybody else. Once we're done, we go to the next one and repeat. Okay? So now we can do 1 and 2, 1 and 3. That's it, we cannot do more. So now go to the next and repeat. You don't have to go back to 1 because we already have that one. Okay? So now the only new length 2 element that comes in is 2 and 3. We are done with that. Now we go to the next one. What's the next length? 3. Well, in this case, when you go to length 3, it's just everybody together, right? And we're done. So if you follow this is only for a finite set, of course. When you follow this process, at the end, you will always end up with the last guy, which is the whole set. Okay? And then you're done. So, do you understand how we build this one? So let's count. How many elements do we have here? 8. Okay. So do number 3. Write them down. Get the feeling in your hands. Write the elements in number 3. Let me take attendance. Daniela Áviles, Andy Brito, Raúl Campos, Brian Cruz, Miguel Díaz, Brian Echevarría, Anthony Fuentes, Ian German, Talía González, Carlos González, Sebastián González, Alejandro Iscaray, Alfredo Llanes, Edwin Mendieta, Mario Núñez, Leonardo Quevedo, Michael Valdez. All right. Did you write them down? How many elements did you get?
16.
16? Yeah. All right. So let's see. Let's do it. So again, following this process, my first guy will be length 0, right? So which one has length 0? When I say length, I mean number of elements, okay? So what will be the length 0 case? The empty set, right? That's the one that has no elements. Now we move to length 1. So we're going to stop when we get to length 4, right? Because that's the length for the number of elements of our set. Okay, so length 1, I have 1, 2, 3, and 4. Everybody okay with this? Now let's go ahead and let's move to length 2. Okay, I'm gonna do it in rows. Okay. All right. So I need to do 1 with 2, Then we can do 1 with 3. Then we can do 1 with 4. And we're done with 1. Go to 2 and repeat. That will be 2 with 3. 2 with 4. We're done with 2. Now go to 3 and repeat. That will be 3 with 4. There's no need to look back because 3 with 2 we already have it. 3 with 1 we already have it. You understand this? You just have to look forward. And then done with length 2. Yes? Now we need to go to length 3. What are the length 3? So it will be 1, 2, 3. Okay. So now, here is a little bit more tricky. And my advice to you is the following. Fix the first 2, okay? And then change the rest and find all possibilities. And then once you're done, then you fix the first and the last and find all possibilities. And then you fix the 2 and the second and the last. You understand what I'm saying? So you want to write all 1, 2 something. Once you're done with that, you want to write all 1, 3 something. Yes? And then all 2, 3 something. Does that make sense? Okay. So let's see. 1, 2, 3. Then 1, 2, 4. And that's it. I cannot write anything else with 1 and 2. Now let's write everything that we can with 1 and 3. Okay? So, because I fixed the 1 and the 2, now I'm going to fix the 1 and the 3. Remember, you always look forward. That's why you have a way to order the elements is good. There's no need to put a 2 in there because I already have that set. So the only thing that we should look forward to is 4. 1, 3, 4. I already did everything I could with 1. Now I'm going to move to 2 and repeat. Let's see. 2 and 1, no, but now we do the pair 2, 3. And that's only 2, 3, 4. Yes? And you cannot go to 3 because if you go to 3, you have your force to go back to make a length 3 because you only have 3 and 4 available. So to make a length 3 set, you will have to use 1 and 2, but those were already used over here. Okay? So that's length 3. And then what do we need? So length 4, which is the whole thing. And we close it up. All right, so let's make sure that we have everything here. So 1, 2, 3, 1, 2, 4, then 1, 3, 4, and 2, 3, 4. Yes, yes. So let's see, let's count. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So let's write this down. Notice that in this case, the cardinality of the power set equals 16. In the case before, the cardinality of the power set equal 8. And then I guess over here, what was the cardinality of the power set? It's 1. And no, 2. And over here, the cardinality of the power set was 1. Right? Let's try to see if we find a pattern. Okay? For example, hopefully you realize that this is 2 to the 0. This is 2 to the 1. This is 2 cubed. This is 2 to the 4. And it turns out that 4, what is 4? The number of elements in A. So this is 2 to the cardinality of A. Same thing's happening here. You see? This is 2 to the cardinality of A because A has 3 elements. That's 2 to the cardinality of A. A has 1 element. And this is 2 to the cardinality of A because A here is the empty set, so it has no elements. Yes? The point is that this is always the case. Now, when we talk about counting, we're going to see why. We're going to prove this later on. Okay? But right now, let's take it as a theorem because it's going to help you out. At least you know when you're done listing subsets. Okay? So, theorem, we'll prove this later when we discuss counting. But right now, let's say if the cardinality of a set A is n, then the cardinality of its power set is 2 to the cardinality of A. In other words, it's 2 to the n. So by saying this, I'm saying if a set is finite, then the cardinality of its power set is 2 to the number of elements of the set. Okay? So a result from here is corollary. So if a set A is finite with cardinality equals to n, so with n elements, then there will be in the homework you have questions like this. Number one, what's the number of subsets of A?
Yeah, he asks you for proper and improper substance.
Yeah, so what's the number of subsets of A? That's just the cardinality of the power set. Remember, the power set is just all subsets together, right? The collection of all subsets. So that's just 2 to the n, okay? Now, what's the number of proper subsets?
-1.
Why?
Because the last one is the same.
Very good. So, if you want to count how many proper subsets a set has, all you have to do is the number of subsets, but remember, this is also counting the whole thing inside, the whole set A. Just take that one out. That's 1 that you have to remove. So that's 2 to the n minus 1. So how many proper subsets this guy has? Well, it has 15 because it's everything that we have here. Just remove this one. Remember, proper means that you are not allowing the whole set to be there. Okay? So you only the smaller guys. So it's always minus 1. So that's your formula, so you can do those little homework problems that you have. Okay? So number of subsets is just 2 to the n, where n is the number of elements. Number of proper subsets is 2 to the n minus 1. Okay? Now you know why minus 1. You're just removing the whole thing, like the entire set. We okay with this? Okay, be careful with the. All right, good. So then I guess let's do a little proof involving power sets. So another theorem, or I guess example. Prove the following. So prove that the power set of A is a subset of the power set of B if and only if A is a subset of B. So let's prove that the power set of A of A and B are sets, some sets. Okay? And let's prove that the power set of A is a subset of the power set of B if and only if A is a subset of B. Now remember, if and only if this is a biconditional. What do you need to do to argue a biconditional? You need to prove two directions. Okay? So recall to prove the statement of the form P if and only if Q, what we do is we prove two things. First, we prove that P implies Q, and then second, we also prove that Q implies P. Because remember, P if and only if Q is equivalent to P implies Q and Q implies P. Okay? So every time that you want to prove a biconditional statement, this is what you do. You need to prove one direction, but then you also need to prove the other. Okay? So in other words, this proof is going to have two parts. First, we need to prove that if the power set of A is a subset of the power set of B, then that means that A has to be a subset of B. Okay? And then we're going to prove the other direction that says if A is a subset of B, then the power set of A is inside, is a subset of the power set of B. Okay? We got to prove those two statements. All right, so solution. So first, we're going to do this direction. Okay? So that means we want to prove that if the power set of A is a subset of the power set of B, then A is a subset of B. We're proving this. And then we need to prove the other direction. Do you understand this? All right. Again, this is an if then. How do we prove if then? Assume P, prove Q, right? So we start by saying assume. Again, here it is understood that let A and B be two sets. This is at the very beginning. Now we're going to assume this part, we're going to prove the other one. So assume the power set of A is a subset of the power set of B. Okay? So we have this. When we're going to use it, I don't know. We will see. Okay? Now, my advice to you is we assume this, we need to prove this. Now, it's always good to write what is it that you want. And that way you're going to get an idea of what you need to do to get there. So this, you put it in a corner. I'm putting it here, but this really you should put it in a corner where nobody sees it. This is just for you. Okay? So what do we want? What do we want to show? So we want to show that A is a subset of B, which is equivalent to say what? That if X is in A, then X is in B. Yes? So we want to end up with the statement of this form being true. This is what I want. So now when you look at what you want, this already tells you what should be your first line. So because this is what you want, how should we begin? So we want to prove that that's true now. So how should we begin? Assume P, prove Q. It's the same idea over and over again. So now my next line is, so remember, this is in a corner, nobody sees this part that is in red. Assume the power set of A is also the power set of B. Now I'm going to let X be an element in A. Because what I want to show is that if X is in A, then X is in B, right? So you just start with an element in A. So now my next line would be, let X be an element in A. Now, the point is that I want to do some work, and eventually I want to end up with this. How? We will see. Okay? Of course, the idea is that somehow we want to use this assumption to be able to get to this other side. Okay? Now let's see. Let X be in A. I know I want to fill in details, and I want to end up with X being in B. Let's see if we can do it. All right. What can we do here? What do you think? All we have at our disposal is our knowledge of the power sets, how they relate. So if you want to use this, right, that's the only thing that we have, then somehow we need to be able to go up to this level. Now, what sort of elements do we have inside these guys? How do they look like? They are sets, right? And what do I have here? Elements. So the first thing that we need to do is we need to make a set out of this. So how can you make a set out of this? Let's put curly braces around, right? So if X is in A, so let X be in A. So then I will consider the set containing X. Where is this guy? In the power set of A. X is in A, but the set containing A, containing X, is now a subset of A. Yes? So let me write this. This is now a subset of A. And what do we use for this? What's the justification for this step? We basically use definition of subset, right? I'm going to put the reasoning, I'm going to put it here. The reason why this line implies this one is because of the definition of subset. Do you understand this? Because X is in A, so this set is a subset of A. But now, if this is a subset of A, this is an element where? In the power set. Now, this tells me that this is an element in the power set of A. You have to be very careful. Notice how I'm switching from subset to element. You have to make sure that when it makes sense to do so. Okay? For example, if you write this, that doesn't make sense. If you're writing a computer program, the compiler is going to scream at you right here. It's not going to compile because it doesn't make sense. There is an element, but this, when you write this on the power set, it's expecting a set, not an element. Okay? So you have to be careful. All right. Now I managed to show that this element, this set is an element in the power set. Now we can use our assumption. If it's an element in the power set of A, what can we say now? It's also an element in the power set of B. That's our jump from A to B. Why? Because of subset, right? Every element here is supposed to be an element here, right? That's what it means. So now from here it follows. I'm going to take a couple more lines. So now from here we get that this means that the set containing X is an element in the power set of B. Why do we know this? Because by assumption, right? So this was the assumption. And assumption slash definition of subset, right? Because we're saying that the power set of A is a subset of the power set of B. That's our assumption. Okay, but now we can unwind. So if this is an element in the power set of B, what can you say about this set? It means that it's a subset of B, right? So then from here, it follows that then the set containing X is a subset of B. Here we use definition of power set, meaning that its elements are the subsets of B. So because this is an element, that means this guy is a subset. But now, if this is a subset of B, what does that mean about X itself? It has to be an element of B because it's a subset. Every element here is an element here, right? Then from here we get that then X is an element of B. Here, what justification do we use for this? Definition of what?
Subset.
Definition of subset. So if you ignore all the in between, now we managed to show, assuming this, we show that if X is in A, then X is in B. You know, by transitivity, we put all of this, and then X in A implies X is in B. Yes? So A is a subset of B. Did you understand this? Now let's do. Okay, do you see how to do it the other way around? How would you do it the other way? Let's say try it, and then on Wednesday we're going to. I'll do it. I mean, just I don't want to take more of your time. I'm like some minutes off. So the other way around would be assume. Let me just write what the other way around would be. So now you want to show that if A is a subset of B, then the power set of A must be a subset of the power set of B. Try to write this on your own, okay? As a whole. So do this as a home. Okay? Remember, you need to assume this, and then you want to prove this. So to prove this, what do? Start with an element in here, and then somehow argue that that element is also here. Along the way, you may need to use this information. Okay? Think about it and see how you can do it.